In the previous class, we have found that even if the system is balanced in the respect of fundamental and the harmonics, the neutral current is still flowing because of triple harmonics, because they do not get cancelled. Rather, they have same phase angle and they get added up. And that's why the rating of the neutral conductor has to be chosen appropriately. Okay, so I hope that point was clear. Now, today we will discuss about the line-to-line voltage, BAV, BVC and VCA. Let us see what is the effect of balanced harmonics on the line-to-line voltages. So we will find out what is voltage BAV, BVC and VCA. So let us first take BAV, then we can extend that idea to BVC and VCA. So what is BAV? BAV is nothing but BA minus BV. You see here, this is BAV, which is equal to BA minus BV. Now what is BA for balance case? BA is nothing but root 2B sin n omega t minus alpha n minus BB, which is n1 to infinity root 2 Bn into sin n omega t minus 120 minus alpha n. Because they are balanced, so the magnitude and the phase angle is symmetrically displaced by 120 degree. If it is n frequency, then it is plus minus n into 120 degree. By expanding this term here, it becomes n omega t minus n into 120 this side, and alpha n is taken on this side. So it becomes n omega t minus alpha n minus 120 into n. Now we have to simplify this and see what do we get. If we simplify this, then we can simply expand. This is sin A minus B. This becomes sin A minus B. If we call this as A and this as a B. So this is sin A into cos B minus sin A cos B minus cos A sin B, minus, and this minus becomes plus. Sin A cos B minus minus plus cos A sin B. So this is cos A and this is sin B. Now we can see that there is one common term between these three terms, and that is about the sin n omega t minus alpha n. So this is common and this is common. But I have to simplify this term first before I combine these two terms. So let us combine these two terms by substituting the value of cos 120 into n. Now what is cos 120 into n? Now n varies from 1 to infinity, as we have fundamental, second harmonic, third harmonic onwards. So let us say n is equal to 1. Then this becomes cos 120 into 1 means cos 120. And what is that? It is minus half. Similarly, when n is 2, it is cos 120 into 2. That is cos 240, which is same as cos minus 120, and which is same as cos 120 that is again minus half. Okay, so if you see, cos 120 is always half, irrespective of the value of n. And when n is 3 or multiple of 3, then this is cos 360, which is 1. We will see that for n is equal to 3 or multiple of 3, this whole expression is actually 0, because this is 1, so this will go away with this, and sine 360 is 0, so this will be 0. So whole term is 0 for n is equal to 369. Okay, so this BAB exists only for non-triplet harmonic components. For triplet harmonic component, the whole term is equals to 0. Okay, we will see it. So this is the simplification for cos 120n. Therefore, we can write that cos 120 is always equal to minus half. So this minus half basically means this becomes minus half into minus 1 here, and that becomes plus half. So plus half and 1, 1 is from here. So 1 and 1 half becomes 3/2. So this is 3/2 as a coefficient of sine n omega t minus alpha n. Now let us see the value of sine 120n. Sine 120n, if you see, then let us say 120 is 1. Let us say n equals to 1. Then sine 120 becomes sine 90 plus 30 cos 30 root 3/2. Okay, and when n is minus 1, then this becomes, or sorry, when n becomes 2, when n becomes 2, this becomes 120 into 2. What is that? Sine 240, which is same as sine minus 120, which is same as minus root 3/2. So you see the sine of 120n changes from plus root 3/2 to minus root 3/2 as n proceeds. Sine 120 into 3 equals to 0. Cos 120 into 3 equals to 1. So using these values, we can write that the value of cos 120n, the value of sine 120n equals to plus minus root 3/2 as n proceeds 1, 2, 4, 5 and so on. So we have written this as plus minus root 3/2. This is plus minus, because sine 120 is first is root 3/2 here. So plus sign is first. When n equals to 2, this is minus root 3/2. Now we will combine these two functions, the cosine and sine, simplifying in terms of sine a minus b. So we will take root 3 common from this and this root 3 common. Then the first term becomes root 3/2 here. and this becomes plus minus half. Root 3 comes outside of this bracket. Okay, now we will simplify this term. Let us call root 3 by 2 as Rn cos theta n, and plus minus half as Rn sin theta n. Then we will square and add, we will get Rn equals to 1, and divide 2 by 1, we becomes theta n, we get dividing sin by cos, it becomes theta n equals to tan inverse plus minus 1 by root 3, that means plus minus 30 degree. So this is the value of theta n. So we can write this as Rn cos theta n into sin n omega t minus alpha n plus, this is Rn sin theta n cos n omega t minus alpha n. This is similar to sin A plus B formula. So this is A and this is B. Rn is common, whose value is 1. So substituting the value of Rn and theta n, we will get this expression. That is, the BAB equals, as a function of time, n 1 to infinity, but n is not equal to 369. For 369, this line to line voltage equals to 0, because the triplen harmonics of voltage will cancel each other. So for non-triplen value of 369, we have the expression of root 3 into root 2 Bn sin n omega t minus alpha n plus minus 30 degree. For n changing from 1, 2, 4, 5, then 7, 8 and so on, the plus minus are assumed alternatively. The plus minus sign are taken alternatively as n proceeds from 1 onwards. And note that for n is equal to 369, okay, the BAB equals to 0, because for 369, actually if you find out, let us say BAB3, you can say BAB3 is nothing but BA3 minus BB3. So what happens? BA3 is nothing but root 2 B sin 3 omega t minus 3 omega t minus alpha 3, and BB3 becomes minus root 3b sin 3 omega t minus 120 degree and then minus alpha 3. So what happens? 3 into 120 becomes 0, and therefore the third harmonic get cancelled. Similarly, 6, 9 or multiple integer of 3 harmonics get cancelled. So what we find here is this, that the value of line to line voltage is therefore root 3 root 2 Bn sin n omega t minus alpha n plus minus 30 degree, where n changes from 1 to infinity, but n is not equal to 369. For n 369, BAB equals to 0. And the sign plus minus here is taken alternatively as n proceeds from 1, 2, 4, 5 and so on. So when I say that n is not equal to 369, what does it mean? It means actually that triple harmonics are missing in the line to line voltage. Triple harmonics are absent in line to line voltage. This is a dual behavior to that of neutral current. In neutral current, the triple harmonics are added up, but here in line to line voltage, the triple harmonics are missing. What is the effect of this missing? Or what is the effect of the absence of triple harmonics in line to line voltage? The effect of absence of triple harmonics in line to line voltage is this, that line to line voltage becomes less or equal to root 3 times of VLN. If you independently measure the line to neutral voltage, RMS value of line to neutral voltage, and you multiply by 3, for a balanced system, this must be equal to line voltage. For a balanced system with fundamental only. But if we have balanced system with harmonics, then BLL is less than root 3 BLN because triple harmonics are missing. So BLL lacks, or BLL does not have triple harmonics. However, the triple harmonics are present in the line to neutral voltage. That's why the RMS value of line to line is less than the root 3 times of BLN. And if you find the kVA rating based on this, then you can see that if I multiply both sides, the line current I and I, then you will see this is nothing but root 3 BLL into I here. So we have multiplied by I here and I here, then this becomes the kVA rating, or you can say line to line kVA rating. So this side is line to line kVA rating, this side is 3 times of line to neutral, or you can say per phase kVA rating. So per phase kVA rating if you take and multiply by 3, then this will be greater than the line to line kVA rating. So now there is a discrepancy that if you design per phase basis, you will have overrated design. But if you design line to line based rating, this will be less than the 3 times of the per phase kVA rating. And the difference is coming because of the absence of triple harmonics. So what do you see here? The behavior of line to line voltage is completely dual of the behavior of the neutral current. Neutral current, in spite of the balance harmonics, will get added up, and hence it is 3 times the RMS value of each zero sequence current, or you can say each triple harmonics phase currents. If you recall from the previous discussion, the IN equals to 3 times of IA0. And therefore RMS value is 3 times of the RMS value of IA0. But here BLL is actually less than root 3 times of BLN. So their behavior is different with respect to the neutral current and with respect to the line to line voltage. So this is the important conclusion from the study of 3-phase balanced system with harmonics. Now let us come to the apparent power. The apparent power for this system must be equal to 3 into B into I, because all three phases are balanced. Because we have a balanced three-phase system. So the total apparent power will be 3 times of each phase apparent power. And this must be equal to P square plus Q square plus D square. The D will come into picture because the system is having harmonics. So distortion power will be the part of the apparent power. The S is no longer true, or S is no longer equal to P square plus Q square for system having harmonics. Okay, so there is one more term called D square to make the equality. So S becomes P square plus Q square plus D square. So there exists a D for which the relationship for apparent power, real power and the reactive power is there. So now what is P here? P is the real power, which is the summation of all real powers for phase A, for phase B, for phase C. If I say that P is the total real power, obviously it must be sum of PA plus PB plus PC. And this Q must be the sum of QA plus QB plus QC. Similarly, the D must be the sum of DA plus DB plus DC. But here they are same because it is a balanced system. There are harmonics, but system is balanced. So therefore, DA equals to DB equals to, you can say, DC. Alright, similarly, QA equals to QB equals to QC in this case, and PA equals to PB equals to PC, which can further be written in the form of fundamental and harmonics. So this is actually PH. We can again resolve into fundamental and harmonic of each phase real power. For example, PA will have PA1 plus PAH. Similarly, PB will have PB1 plus PBH. So we can combine all the H or harmonic real powers together to make it PH. So the overall real power will be sum of the fundamental and the harmonic real power. What is pH? pH will be P2 plus P3, P4 and so on. And this is the fundamental power. So fundamental plus remaining power. This whole term is called the harmonic real power. So we can add this term as pH. Beta n minus alpha n. Fine. Similarly, we can write for the reactive power, which is the sum of Q1 and QH. As you can see from this is Q equals to Q1 plus QH, and QH is nothing but Q2 plus Q3 plus Q4 and so on, and this is the fundamental Q1, which again can be written in the form of series for n 1 to infinity 3 into Bn In sin phi n. So this is 3 Bn In cos phi n, this is 3 Bn In sin phi n. This is similar to the single phase system. The only difference is 3 times because it is 3-phase system, and also there is a Bn In because there are harmonics and fundamental. Clear? So these two expressions are the expression for real power and the reactive power. So this is the story of 3-phase balanced system. That for 3-phase unbalanced system, we will have sufficient rating of the individual conductor, and line to line voltage will be less than root 3 times of line to neutral voltage. Okay, and the expression for real power and the reactive power are basically 3 times of Bn In cos phi n and Bn In sin phi n for n1 to infinity. Now let us consider the most generalized case. That case is basically unbalanced non-sinusoidal three-phase system. This is the most generalized case where we have unbalance in fundamental as well as we have unbalance in the harmonics. Fine. So that means to say that unbalance is in respect of fundamental as well as harmonics. Earlier, what we considered only fundamental unbalance, then we considered the fundamental balance and harmonic balance. Now this is the third case where fundamental is also unbalanced and the harmonics are also unbalanced. How do we represent it? It is shown in these equations. As you can see that the voltage is now having a different magnitude. This is BAN, this is BBN, this is VCN. They are not same. Earlier we have a same voltage BBB or BN, but now they are having different magnitude. Similarly, the phase angles are not symmetrically displaced by 120 degree, rather alpha AN, alpha BN and alpha CN. So this forms the voltage BA, BB and BC. Clear? What about the currents? The currents are IA, IB and IC. So you can write the expression for current as well. Root 2 times the RMS value of that phase current IAN and then sin n omega t minus beta AN. So beta AN is the phase angle of the current IA. Here n for harmonic, not neutral, and first the harmonic number 1 to infinity, and IV root 2 into IBN sin n omega t minus 120 degree. For B phase, omega t is replaced by omega t minus 120. Remember it, this omega t is replaced by omega t minus 120. So n is outside, n omega t minus 120. And then minus beta Bn, because it is unbalanced current. So this is minus beta Bn. This is not simply beta n. For phase C, root 3 ICN sin n omega t plus 120, because this is phase C, and minus beta Cn. So you see that all voltages and currents are having a different magnitude, RMS values and unbalanced phase angles. Similarly, currents are having different magnitudes and unbalanced phase angles. That's why this is the most generalized case. And for that case, we will find out all the terms that we have discussed earlier, starting from the active power, reactive power, then real and reactive powers, and then power factor, apparent power, and so on. So let us start with the instantaneous power, which is the beginning point of all power expressions. So this P3 phase actually is PT. 3-phase instantaneous power is BA into IA plus BB into IB plus BC into IC. Or you can say PA plus PB plus PC. We can solve for one phase and then we can interpret for phase B and for phase C. Okay. So let us start with the phase A. Now phase A, instantaneous power is BA into IA. So this is actually BA whole thing, and this is IA. This is the multiplication of two sine series. This is similar to what we have done for single phase system with distortion in voltage and currents. Almost same. So you can directly tell that if we multiply these two voltage and currents, what shall we get? We will get a series of P active and P reactive, and then we will get the P rest powers. DC component is not there here, otherwise you will also get the DC component. So if you multiply these two terms, there will be similar frequency component who will interact together to form active and reactive powers. So if we multiply the similar frequency term, we will get first P active or PAN. So this will be P active, BAN, IAN cos phi AN, 1 minus cos 2 omega t. But here omega t will not come, but come n omega t minus alpha AN, because the A phase voltage has the sign argument of n omega t minus alpha AN. So twice of that. So this term is actually cos 2 omega t equivalent for single phase system. Since it is unbalanced, so alpha and AN will come here, and omega t becomes n omega t, so this becomes n omega t. That's how it is being n omega t. This becomes n omega t, not like this. Twice n omega t minus alpha. And 1 minus cos, because of the collecting the coefficients of cos and sine. Okay, so this becomes 1 minus cos 2 n omega t minus alpha n. You can solve yourself and verify, you must get the same expression. Then next one will be P reactive. Now P reactive is again BAN IAN sine, okay, in bracket sine phi AN. This is the equivalent to, this is the counterpart of cos. So this is BAIA cos, this is BAIA sine, into sine 2 omega t. Now 2 omega t becomes n omega t minus phi alpha AN. So this is sine 2 omega t term. And therefore this form P reactive. And this part is basically nothing but QAN. This is PAN, where n is 1 to infinity. And then we have remaining terms of this power, we call it PA rest. So rest component will have this voltage term root 2 BAN sine n omega t minus alpha AN, where n varies from 1 to infinity, and into h equals to 1 to infinity, but h is not equal to n. This is beta h omega t here minus beta AH. Close this and close this. This is called PA rest. So we have P active, P reactive and PA rest. Now the same thing is true for B phase and for C phase. What is phi AN here? Beta AN minus alpha AN. The phase angle of current of nth harmonic minus the phase angle of voltage of the voltage harmonics. Now this expression can be extended for phase B and for phase C. For phase B, the only difference will be A is replaced by B, so A becomes B, and omega t becomes omega t minus 120. Okay, accordingly, we can simplify the expression for B phase. That's good enough to tell you what you will get. So this is the first term, sigma n1 to infinity b Vn I Vn cos phi Vn 1 minus cos 2 omega t minus alpha Vn. So because of B phase we have omega t minus 120 degree here, and this is basically PB active, this is PB reactive, this is PV rest, and this value is nothing but QBN. This is PBN. Extend the same concept to C phase. So C phase you will get here BCN ICN cos phi Cn, n is changing from 1 to infinity, 1 minus cos n omega t plus 120 degree. For C phase, omega t becomes omega t plus 120 degree. So here omega t will be replaced by omega t plus 120 degree, and B is replaced by C. So this becomes C here. So this is again PCN, and the whole thing is PC active. This is QCN, the whole thing is PC reactive. So P active is this, P reactive is this. This is PCN, this is QCN, and this is nothing but PC rest. Okay, so these are the three phase powers for three-phase system with unbalanced, harmonics and fundamental. And if you simplify this to find out the real power will be the summation of the constant terms, because if you integrate over a cycle, all time bearings will cancel. What is left out is the constant terms like BAN IN cos phi AN, then BBN IVN cos phi VN, then BCN ICN cos phi CN for n varies from 1 to infinity. The rest of the terms will be equal to 0 if we integrate over a cycle using this relationship, that Pt equal to 1 by T 0 to T Pt dt. So what is Pt here? Pa plus Pv plus Pc, and each has one constant term, that is BAN IN cos phi n. B phase has constant term BVN IVN cos phi Vn, and this C term has term BCN ICN cos phi Cn. Or we can write PAN plus PBN plus PCN. Similarly, we can write for the Q. The Q is the sum of the peak of the P reactive of each phase. That is basically QA plus QB plus QC. So QA is VAN IAN sin phi AN, and QB is BBN IBN sin phi BN, and QC is BCN ICN sin phi CN. If we add them, we will get the total reactive power, that is QAN plus QBN plus QCN. This is N here. Okay. So what is the total real power in terms of the fundamental and harmonics? So we can write that this PA equals to PA plus PB plus PC, and each real power has the fundamental and harmonics. So I can write PA1 plus PA1 plus PB1 plus PC1 plus PA2, PB2, PC2 and so on. So this will form actually P1, that is the fundamental real power of each phase, and then P2 and then P3 and so on. So here this P1 is consisting of the A phase real power, B phase real power and C phase real power at fundamental frequency, voltage and current. Similarly P2 and P3. This can be further written in the shortest form as the fundamental power P1 plus PH. What is P1 here? P1 is here the fundamental power of each phase, and PH is the total harmonic real power coming from the harmonic components of voltage and currents. In the similar way, we can also write for the reactive power Q. So Q is nothing but QA plus QB plus QC. As you can see that QA, you can add one more term here, equal to QA plus QB plus QC, where QA has terms QA1, QA2 and so on. Similarly, QB has QB1, QB2 and so on, and likewise QC has those terms. Now we can group into the fundamental and the remaining harmonic component. For example, we can write QA1 plus QB1 plus QC1 and then QA2 plus QB2 plus QC2 and so on. Then we can combine this fundamental component as a Q1 and the remaining component as Q2 and Q3, and these can be further combined as QH. So this is the QH reactive power. This is the fundamental reactive power. So we have resolved these real and reactive powers in terms of the fundamental and harmonic components, where each includes the corresponding phase components. Now with this understanding, we can proceed further to find out the apparent power and distortion power and the power factors and so on. So that I will continue in the next class.